All right, so we are skipping chapter 5, moving on to chapter 6. We're going to be moving on to work and energy. And so here we're looking at work. And so we're going to kind of define work in a very basic form. Work is defined as, or something that has energy has the ability to do work. That's a very basic sort of way to define energy and relate it to work. In order for work to be done, the force and the displacement need to be in the same direction. So I'm basically going to say that work is equal to force times distance. I can just express that as like delta x. But the key point, though, is that they must be parallel to each other. Okay, so it's often expressed in this sort of way. Put a little parallel symbol there, kind of like as a subscript. The force that is parallel to the displacement that is occurring. So if we look at this drawing, this woman is applying a force in this direction, and the box is going to slide along the floor in this direction. So what needs to happen is we're going to break this force down into its x component, and it's the x component that I'm concerned about, and we'll take that x component and multiply it by the x component of the displacement. The textbook kind of sometimes might express things a little bit differently, but I'm not too concerned about it. The bottom line is figure out how much of the force is in the same direction as the motion, or another way that it can be done, which I don't like as much, is you might sometimes find that they will use the force, the entire force, and figure out how much of the displacement, make a right triangle, how much of the displacement is in the same direction as the force. I'm not a fan of doing it that way personally. It's more intuitive to do it, figuring out how much force is in the same direction as the displacement. So if she is pushing or pulling in this direction, only the amount of force in the x direction is actually going towards doing the work. Mind you that because you have a force of gravity, right, I'm just going to call it mg, acting down, and you have a normal force acting up, do you recognize that the vertical component of her force is actually unweighting the object? So the normal force wouldn't have to be as large. I'll just make it a little bit smaller in that way. So by making it smaller, remember that the force of friction is equal to uk times the normal force. Well, if we are decreasing the normal force, then we're going to also decrease the force of friction. So it actually makes it easier for her to pull it. And so at first glance, it might seem like pulling up at all at an angle might be wasted. The vertical part of her force is kind of wasted effort because it's not translating into her actually moving it left to right. However, it is unweighting it and making the force of friction smaller. So in full truth, the easiest and most efficient way to pull something across the floor is to actually lift up a little bit, and there is a certain angle at which you have the most efficient angle to pull. So pulling perfectly horizontally is not the best method. Pulling at an angle is actually the best method. Okay, so with all of that said, let's kind of move on just a little bit, and I'm going to move on to this concept. So we have a man carrying a bag of groceries, from one place to another, and the idea here is that he is not doing work by carrying the groceries around. In the first moment, let's say he's standing still. In the very first moment that he takes that first step and gets up to speed, sure, in that moment he is doing work, but he is not doing work once he's up to that speed and maintaining a constant velocity. He's not accelerating, he's not lifting the bag or lowering the bag. No work is done. He is applying a force upwards. However, the bag isn't moving upwards. So therefore, there's no displacement in the y direction. He is not doing work in the y direction. Is he doing work in the x direction? Well, as I said, there is no force in the x direction, no net force anyway, because I'm basically assuming that the friction is essentially negligible in the x direction. He's not running, there's not really any significant air resistance and that sort of thing. So there's essentially no work being done in order to carry it across the room. What are the units for work? It is, since it is force times distance, this is the way it's often written, or it can be delta x in either case. But it is a newtons times meter measurement, which is the same thing as joules. Okay, 1 joule is the same thing as 1 newton times meter. Keep in mind that the newtons and meters are parallel to each other. That is kind of crucial, like later in the year, because this is what's known as a dot product. There's a good video on Khan Academy on the differences between dot products and cross products. So dot products occur when you're only looking at the value of the two things that are parallel to each other, that are acting in the same direction. Cross products are when you're looking at the two things that are perpendicular to each other. So just to give you a little heads up that later in the year, we're going to be looking at something called torque, which is going to be a rotational force. So let's say we have some sort of thing that's going to pivot about an axis, and I apply a force here. So here's my force, and then here's the distance. These two forces, or these two things, are perpendicular to each other, and I'm only concerned about the amount of force that is perpendicular to the distance. And so this will also have units of Newton meters, but that's later, and it's very different. Okay, so it is very rare that work is expressed in terms of its, basic units of Newton meters. Instead, it is expressed in terms of joules. That other thing that I was just talking about, torque, that is expressed in Newton meters, and it has no shortened version to it. So they are two different things, so make sure you keep those things straight. So, joules are the units for work. Remember that, again, work is only done if the force and the displacement are in the same direction. So, in this case, there is no work done keeping the moon in orbit. There is a force that is towards the center of the Earth, and there is its displacement is along the tangent. It is perpendicular to the force, so there is no work being done in order to keep the moon in orbit. This is, since we skipped chapter 5, maybe this doesn't make a whole lot of sense right now, but basically a centripetal force is a force that acts towards the center for something that is a circular moving body. Okay, moving on. So if we were to graph force versus distance, then taking the integral of that, and while I realize this is not a calculus-based course, the integral is essentially just taking the area underneath the curve. So I've kind of expressed this before. You're essentially just taking, since I have an equation or a formula where work is equal to force times distance, well, put force on the y-axis, put distance on the x-axis, and you figure out what the area is between the x-axis and the curve. That area is going to give you force times distance, which is work. So it'll give you the work done. You can have a positive versus negative work, and you would have to treat those as positives and negatives accordingly. Okay. And I talked about that. I'll skip that for a moment. I think. See if it'll let me. Oh, it did. Okay. There we go. Sorry about that. Okay, so so here's the part that I really want to get to, is this equation here, where kinetic energy is equal to 1/2 mv squared. And in the AP test, rather than putting KE, they just put a capital K. So they will just write it like this. K is equal to 1/2 mv squared. I will write it as KE, just out of old habits, I suppose, and it keeps consistent with our textbook. Here, it is expressing the net work that is being done any positive versus negative bits of work that can be done. So there is the net amount of work that is done on a system. If I were to lift a bag, bag of groceries, if I were to lift a bag, I am doing positive work onto that object. And if I were to let it down gently, then the earth is doing negative work onto that object. I'm not doing the negative work, but the earth would be. So the net work is equal to the change in kinetic energy. This is known as the work energy theorem or principle. And what it basically says, and since work is equal to force times distance, and kinetic energy is equal to 1/2 mv squared, remember that's, since it's delta kinetic energy, it's delta V. So let me go through an example of how this applies. And this is my favorite example. If you have a car that is moving at some speed, let's just say that it's 20 meters per second, or 20 miles per hour for the school zone is usually the example I will use. So that's your velocity, okay? Let's just say that it's 20 miles per hour. I'm not concerned about the units at the moment. Given that you have some velocity, of course the car has a mass, but I'm not concerned about what that is because that's not going to change as time progresses. Given that you slam on the brakes, there's going to be a certain amount of friction force. You slam on the brakes, whatever the friction force that is capable between the brakes and the tires, that friction force is going to be the same whether you're moving at 20 miles per hour or 30 or 40 or 50 or so on. The friction force is going to be the same regardless. So here's what I want to ask. If I were to double my velocity, what would happen to the displacement, the stopping distance? Let me bring this whole thing down. So, just rewrite it like this, where I've got velocity in the parentheses, and I'll do the same thing here with the stopping distance. If I were to double my velocity, 2 squared is 4, so I've effectively changed, in fact I only need to put the equal sign there, I've effectively changed the right side of the equation by a factor of 4, which means I must change the left side by a factor of 4. So that means that if you were to double your speed in a car and slam on the brakes, you now have a stopping distance that is 4 times greater. And this is a typical application of the work energy theorem or work energy principle. So if you go from 20 miles per hour in the school zone to 40 miles per hour in the school zone, your stopping distance isn't twice as far, it's now 4 times as far. So keep Bobby safe as he runs across the road in front of you. Okay, so let's see if I can get to an important point here. So force times distance, there's a certain amount of work done to push the nail into the wood, so the force times the distance that it goes in, that gives you how many joules of work you've done. And this is what I really want to get to, is the other thing where the potential energy of a gravitational system is equal to mgy. So in the textbook they use PE for gravitational energy, or potential energy I should say, and on the AP test they use a capital U. So they will do it like this. U is equal to mgy. That's the way it's expressed on the AP test. All right. Potential energy can also be elastic potential energy. So there's the energy in a spring. Compress the spring, release it, and the thing goes flying off. And so if I skip along here, we have something known as Hooke's law, which it says that the force of the spring is equal to negative kx, where K is known as the spring constant. It's also called the stiffness constant. It's basically how stiff the spring is. So it's a coefficient. It has no units. No, it does have units. Excuse me. Sorry. It's newtons per meter are the units. If I divide each side by x, right, my spring constant will be newtons per meter. So I was thinking of friction coefficients for a moment. So the spring constant, newtons per meter, are the units there, and it basically expresses how stiff the spring is. If I were to displace it 1 meter, and at 1 meter I'm applying 1 newton of force in order to make it displaced that much, then it would have a spring constant of 1 newton per meter, which would be very, very low. Most springs are going to be much higher than that. And that's known as Hooke's law. The equation for elastic potential energy is 1/2 kx squared. So again, notice that as you displace it further, the potential energy will increase at an exponential rate. And again, if you were to graph the force versus displacement, the work done to displace that spring some distance will be the area underneath this. Now again, if I apply the work energy theorem, I can say that the work done to displace that spring is equal to force times distance, although keep in mind that the force is increasing throughout that time. So, but if I could actually measure the force at increments, like with the vernier equipment that we'll use, we could say that that force, the average force over that distance, is equal to 1/2 kx squared. Or let's say that I've got a certain amount of energy in the spring, like the one that we were looking at earlier. If I go back to it, yeah, this one. So it's going to go releasing this ball. So if I have energy built up here of 1/2 kx squared, here's a simple and very important concept in physics: the conservation of energy. So if I write it up here, the energy at position 1 is equal to the energy at position 2, and that's the sum of all energies. Then the kinetic energy plus, let's say, that's potential energy. The potential energy plus the kinetic energy, so let's just say 1/2 mv squared. Oh wait, it's not moving. That's fine. I did not mean to do that. Sorry. That's at position 1. That's going to equal the 1/2 kx squared plus 1/2 mv squared at position 2. Well, if this is position 2 and this is position 1, at position 1 it doesn't have any kinetic energy. At position 2 there's no elastic potential energy. So you can essentially say that the energy of the system here in potential energy equals the kinetic energy of the system here. You can figure out how fast this thing's moving when it's released by the spring, given that there's no energy dissipated into heat, which we can get into later. Or I could get into it now. There's no reason not to. If there is heat in the system, let's say that this thing's vibrating and there's heat left in the spring, I just add it in. After the event happens, there's heat energy. I can just put in a capital H. It can be expressed a few different ways. But I can just say, oh, there's this energy that is left in heat, and you just literally add that in. We don't usually solve those problems in AP Physics 1, but it can be done on occasion, where we essentially say, hey, if the ball leaves at this velocity, it actually leaves at a velocity lower than its potential had. So how much heat was produced in the system? You just solve for that. Put in your variables and solve for the heat that was produced. So you can actually, this is something that's usually looked at a little bit more in AP Physics 2 a little bit. You actually look into how much heat is actually produced in the system and things like that. Okay, and I'm going to try and finish up things fairly quickly here. I'm just going to say that when you do have heat, it's usually produced by things that are known as non-conservative forces. Non-conservative forces are forces that are not conserved. So that'd be friction and things like that. But energy is not ever lost. It is put somewhere. If you can't find where the energy went, it's usually in the heat. So here's some of those non-conservative forces. Typically friction, air resistance, those kinds of things are what we are going to look at. Let me finish up on this final thought. Here's a very common application to these sorts of issues. If I have a sloped ramp with a box of some kind that is at some vertical height, and it's the vertical height that matters only. So it has mgy, where this is obviously my delta y. it has some amount of potential energy. The box slides. I meant that box to be separated from that, so let's try it again. Okay, so the box slides through, and let's just say that it's frictionless. When it gets to the bottom, it has kinetic energy. It has no longer any potential energy, so now it has 1/2 mv squared energy. So the typical application here is to solve for the final velocity of the box as it comes flying off of the ramp. In fact, the way it usually goes is something like this. Here's a problem. Here's an AP problem. If the box slides down the inclined plane frictionless and then comes off of the table, mgy, 1/2 mv squared, find the final velocity of the box as it comes flying down this ramp. I am only concerned about this as my delta y. Then, that's part one of the problem. Then, once it comes flying off of the table, figure out how far from the table it lands. And so you would use kinematics to solve for that. You know, you look at the height of the table, how much time is it going to take to hit the ground, and so on. To be perfectly honest, normally it's hitting another box, there's some sort of collision, and that is a momentum problem. That is something that we will look at in the future, so look for future videos on that. That's a typical application. Let me know if you guys have questions.